So, jetzt würde ich dann gleich direkt weitergehen. Mark, to your presentation. So, Mark hat einen sehr interessanten Use Case, den er mal einfach zeigen würde und wie beim MPI-CEC mit dieser Frage der großen Datenmengen umgegangen wird.
Dann, ich werde auf Englisch wechseln, wenn es okay ist. So, yeah, so this presentation was prepared by myself and Mr. Aviral Ved. Both of us are employed at Max Planck Institute of Chemical Energy Conversion in Mülheim an der Ruhr. What it's going to basically describe are the challenges in managing data in a multidisciplinary research organization. And this is part of the sort of, it's explaining the diversity and the problem statement that we're facing and sort of the motivation for why we want to implement a data lake, which we're planning to do in the next year. So first to start, what we're sort of hoping to achieve, we have this like vision. We want users to maintain as much as possible to maintain their existing workflows. We don't want to force them to change so much about the way they work. They're comfortable how they do things, yeah? And this is important for adoption, but really what we wanted to have that, and then in the meantime, their generated data is automatically digitized and categorized for them, such that it is subsequently available and easy to find at a future time. Yeah, and this will bring a lot of benefits with it if we can achieve this sort of vision. We were kind of thinking, and I'll sort of get into little details of how diverse our organization is, but in principle, we're an experimental research organization focused primarily on chemistry and catalysis. This actually means like we go and synthesize things and do experiments on physical objects. And to manage all the data aspects, data assets and artifacts that come from this process, we sort of envision sort of 4 pillars. One is on the far left here, the experimental workflow. This has to do with samples. Samples are like the objects of study. The laboratory notebooks, which are used to document these, and then also data analysis tools. There's also tightly integrated with that lots of activities towards laboratory management. These are also very important for traceability and auditing of research activities. And this is often carried out by technicians. This involves taking inventory, managing measurement instruments, scheduling instruments, and so on. And then we think about the data lake. The data lake is the part where we just want to, like Julian pointed out, just kind of dump all these data artifacts that come from our operations. This will be important for also long-term backing up and archiving. And key here is that in order to make this a data lake rather than a data swamp, we really intend to have a lot of rich metadata for all of these data artifacts to make them searchable and reusable at a future time. And then in addition to that, there's things like project management. So as a research organization, we write a lot of proposals and research projects go through phases, and these result in sort of publishable objects that go onto public repositories. So we need a way to sort of manage that as well, and often push from our local resources onto some public-facing repository. So this is kind of the scope of what we envision. A little bit about our organization, so Max Planck Institute for Chemical Energy Conversion. So yeah, our research discipline is catalysis for chemical energy. This involves things like water splitting, biocatalysis, chemical production. A lot of what we build or what we research, we intend to one day sort of move it towards application and industry to deal with a lot of the issues with renewable energy and sustainability. Our organization, we have at the moment 218 active researchers. These are divided into 22 research groups and 3 departments. Yeah, to give you sort of a more detailed picture of what day-to-day life looks like, and what kind of requirements these people have. So here's an example of a synthesis lab. this kind of work focuses on creating new chemicals or materials. A typical workflow would involve something like planning an experiment, performing a synthesis, characterizing what someone synthesized, analyzing then the results of the characterization. So the characterization generates some raw data, and then these need to be analyzed to sort of determine properties of the object that was synthesized. Then often a person iterates, does this over and over, changing some parameters along the way, and then at some point might also test in an application. The major challenges here are that this person doing these activities, they're very multidisciplinary. They have to interface with a lot of other specialties. Data is generated at a lot of different locations by a lot of different people within the organization. And so to harmonize the data artifacts and link them all together is somewhat challenging. Another use case are people who focus on specialized characterization. So, as I said, when someone produces an object to be studied, like a sample to be studied, it can be measured by multiple different methods. And this example here is an electron microscope. It's quite complex, the instrumentation, and the people who operate this and focus their, where this is their expertise in their domain, they really focus a lot on in-depth analysis. So they focus a lot more on sort of performing the measurement and analyzing the data, more so than the people who are involved in synthesis. And so their workflow looks slightly different. So they often take a job request from someone. They might plan back and forth with the user how best to allocate the instrument time. They'll receive samples from lots of different people, so they have to deal with sample management. And they also have to sort of ensure that the data generated is somehow associated with that sample. So there has to be a sort of relationship between the data outputs here and other entities within our organization. They have to deal with scheduling of the equipment, data analysis, often also keeping track of what algorithms were utilized in transforming a data set during the data analysis. And then, of course, returning the data to the requester. Some of the major challenges here is the data analysis, keeping track of what are the inputs and the outputs of any kind of algorithms that are applied, and also harmonizing any data or any information that they've contributed to the entire research workflow, harmonizing this with all the other stakeholders' note-taking tools. Okay, another use case is similar but different. So it again involves performing data analysis. So this is an example of an NMR instrument. And these tend to focus on more routine measurements. Often people, the actual data owner or requester of a measurement is also the same person who performs the measurement. So we don't necessarily need extra permanent expertise on NMR machines to perform the measurements. Yeah, there's a lot of instruments like this as well, infrared spectrometers and things like this. So there are a number of use cases like this. The schedule in this case, or the workflow in this case, involves scheduling the instrument, performing the measurement, retrieving the data, and analyzing the results. The challenges are quite similar. They need to harmonize their whatever outputs come from this instrument with other data artifacts that are generated along the entire pipeline of the research project. So they need to associate data with samples and experiments and things like that. Another requirement is sort of more towards the application testing. So, for example, people generate or synthesize catalysts, and they want to see how well does this perform as a catalyst in a chemical reaction. And so we have testing facilities for this. These people really tend to focus on the application of what is synthesized, as well as sort of testing parameters. So they might put in a sample and measure for weeks on end on a single sample and see how it performs over time. So a plan here usually, or workflow here usually involves, again, planning, scheduling, measuring, although the measurement takes a long time, and then retrieving the data afterwards and analyzing the data. And the challenges here are the analysis, sort of consolidating a whole bunch of different data streams, and then linking again the data and the sample conditions. Hold on a second. Here we go. One last example is large facilities. So these would be like particle accelerators, like synchrotrons. We have a couple of them in Germany, in Berlin, and in Hamburg. But also internationally, people travel to these. They'll travel to Japan, to the United States, to France, wherever. And these are primarily focused on characterizing a material, so like doing measurements to determine properties of the material. The workflows typically involve planning, but on a longer time scale. So usually you submit a proposal 6 months ahead of time, at least. Then scheduling the measurement time. And then you'll travel to this location, you perform a week's worth of measurements. You take this data back home with you and then spend some time analyzing it. Some challenges here are that there are large data sizes, and to integrate all of the information about what was done on site at this location with other data artifacts that are maybe stored at the home location. Yeah, so I think it's quite clear, though, the workflow depends on the research. The synthesis-centered ones, their main challenge is sample management and making sure that the data stays somehow related to the sample. Analysis-centered main challenges are like data conversions and analysis versioning. In pretty much all cases, it's important to retain links between data generated at different locations and at different times. Yeah, so from these sort of description of our use cases, we come across some sort of problem statements, and I think I've got 5 of them listed here. So one of the problem statements is that data is spread out across different machines and is often very unstructured. The knowledge cannot be automatically extracted from it, and tools cannot be, at least economically, built to automate regular processes. Yeah, so a lot of this has no really formally defined structure. So anytime you would want to build a tool that can sort of automate the boring stuff, it would always be kind of ad hoc. And a lot of rework over and over and over if you wanted to do this and satisfy all of our different users. So it's not really scalable. And the primary reason is the structure of the data. So another problem statement is that researchers spend too much time on repetitive manual work related to generating data, processing data, and publishing data. And yeah, this really slows down their research process and wastes a lot of valuable time doing tasks that can really be, in principle, automated. Solving this would, of course, save time, it would reduce errors, and it would also make better use of resources by minimizing rework. An additional problem statement is that users generally do not have easy access to all of their data assets, either because it's scattered all over the place, maybe on this network drive here, on some cloud server there, on some local computer there, buried inside of deeply nested folder structures, almost impossible to find, certainly not easy to find. Solving this would be amenable would enable users to access their data from anywhere at any time. And this improving accessibility would, once again, just speed up the whole process of research because they wouldn't spend so much time looking for data assets that are already stored in the system. Another problem statement is that it is difficult, sometimes impossible, to trace back the origin of a research result. So, for example, something gets published, there's some result, and some person says, hey, I can't reproduce your result. How did you ever come up with this? It's often the case you just can't trace it back because the metadata hasn't been, the lineage of the data and how it was arrived at was not really carried throughout the whole process. If we could solve this problem, This would allow users and an organization to have complete traceability and reproducibility over all their data artifacts. This would just generally improve management and specifically scientific audits. This would also improve kind of knowledge retention and people sort of reusing scientific results at future times. Another problem statement is that the organization's data assets are not suitable for large-scale analysis algorithms. So kind of in the spirit of being AI ready, our data is not suitable for AI right now because we can't just sort of run algorithms to mine the data or to find patterns in it because it's just too scattered and unstructured. So solving this problem would kind of future-proof to some degree our organization's assets and open up research opportunities. So for example, currently we don't do much in the way of artificial intelligence development, but if we were to have data assets better structured, this would open up opportunities for new research projects to do that. Yeah, so that sort of sums up our main problem statements. Our sort of strategy for trying to solve this is we started a research data management unit at our organization. First step is just to try to promote people to start using electronic lab notebooks. This phase is coming to an end. It's gone pretty well. We've had a lot of buy-in, and we're hoping to be implementing this institute-wide within the next 6 months. We realize we need some very sophisticated data management system. An important part of this is the data lake, and that's phase B up here. We're going to be embarking on that also within the next year. Yeah, in cooperation with GVDG and Julian and his team. We're looking forward to building something really cool there. Yeah, and in addition, there's some other things like to be done. We're also engaging our workers, our researchers in further education. So just trying to give them all the skill sets that they're going to need in order to effectively interact with this data architecture. So we're doing this by subscriptions to online learning platforms and basically stimulating, like providing curricula and course content for them to follow. Yeah, so that basically summarizes where we are right now and what we hope to do within the next year and a half. And I hope I've sort of clearly demonstrated one use case where I think data lake would be a huge improvement to our data management problems. So I want to thank everyone for their attention, and I would welcome any questions.
So thank you very much for your talk. First of all, that was really interesting. Maybe you guys have some questions for Mark. I personally found it really great to see that this new unit is created for data management. So it has been recognized the importance of this data management. I think it's pretty rare to see that happening. So now we see some comments here. Thomas.
Yeah, I'm pretty happy about that too, Julian.
So Thomas.
Yeah, this is Thomas Steinke at SUS Institute Berlin. Thanks for this interesting talk. I have a question related to one of your challenges, that is managing these large data set you get from these external in-depth facilities you mentioned. What is your current process to take? I guess these are data sets in the terabyte region. How you deal with that today, and what are your plans to make that even smoother for the scientists to get the data to your site? Or did you consider to leave the data on the facilities?
Yeah, indeed. So unfortunately, this is also quite a hodgepodge of different options and restrictions. So we have kind of two different types of use cases here. One of our directors has and operates a permanent beamline at a synchrotron. So dealing with that is not as challenging because yeah, we can sort of directly access network resources at that synchrotron. And so anything that's so huge that we don't really want to be moving it around, we can easily leave it there, and that's generally not a problem. There are other cases where people travel to synchrotrons, and each synchrotron has their own kind of regulations and restrictions onto what kind of outside access is allowed or provided. So in many cases, what people currently do is they'll bring with them some kind of storage medium, and they'll just copy everything onto the storage medium and then bring it back home with them and then ingest it into our own system. We may have to continue doing things like that. Some maybe more will present a sort of formal workflow for doing this, such that it gets ingested into our local infrastructure in a way that preserves a lot of the metadata, so in a sort of formal, destructured way. There are, of course, activities going on currently throughout the world at these synchrotrons to some sort of new concepts where the data stays where it's generated, especially for the large data sets, and then they provide sort of computing facilities so that people can access their data sets and run the data analysis on the synchrotron's computing resources, and then what they would take out of that would just be the results, and the results might be stored locally, and these would be much smaller data sets. But it really, like I said, it depends on sort of what's happening at each of these individual facilities. So at the current time, there's no sort of uniform solution to solve the problem.
Thanks.
Okay, great discussion. Anything else? We still have time. Okay, I mean, there can be also later questions raised anytime, as we have also discussion slot. So then, thank you, Mark, again.